Good afternoon, students. Let's begin today's new lesson. In this session, we will discuss the assignment problem. We note in the preceding lessons, we have learned BIP program, maximum integer program, pure integer program, and assignment program is a special type of integer program. So in this section, we introduce the Section 7, the assignment program model. Section 8, solving assignment program, Osborne Hungry method. Now we see an example, prototype example. Prototype example 1. They are focused tasks, task 1, task 2, task 3, and task 4. And they are exactly 4 workers who can finish the tasks. The time each task is finished by the different worker were listed in the following table. We note in this table, this column is worker Anne, Ian, John, and Sean. And this number is the tasks. Task 1, task 2, task 3, and task 4. And the coefficient is the time each task needed per each worker. And the last column is per hour wage of each work. Now in this program, the problem is to determine how to assign the workers among the tasks in order to minimize the total cost. So we set up this program model. And we set up this program model. First, we prepare to some calculations. So we use this column times this wage, and we get this column number. And this column number is the each one to finish task 1 has total cost. For example, Anne finished the task 1 need $419 cost, and so on each other numbers. Now we see the formulator of this model. We set a decision variable is xij. Xij equals 1, the ith worker do this task. 0 is otherwise. So we have the decision variable is x11, x12, x13, x14, and so on, x44. Each decision variable is means each worker to finish task need the total cost. So we get the objective function is minimize z equals this total cost times decision variable x11, x12, x31, x41, and we get this total cost. And this total cost is each worker finish task 1 need a total cost, and we times this column number. Times the decision variable, and we get this total cost on the task 3 and task 4. So we get the total cost of this program is this formula. Now we see the constraint. The constraint is, we see in these programs, each worker only finish 1 task, and each task only need 1 worker to finish it. So it's 1 to 1. So we write as this is the each one finished 1 task, and this means that each task need only worker to finish So we get these types of constraints. So we summarize the model of this problem is, we notice in this model, there are relatively more decision variables. We note that it is more than 16 decision variables, and the constraint is relevantly more large. And we note that these problems include 1, 2, 3, 4, and 7 constraints. So if we solve by general method, its computation is very, very large. So from these examples, we give a definition of assignment problem. Number 1, the number of assignee and the number of tasks are the same. We denote by n. Step 2, each assignee is to be assigned to exactly one task. Number 3, each task is to be performed by exactly one assignee. Number 4, there is cost Cij associated with assigning I to performance or to finish the task J. Number 5, the objective is to determine how or an assignment should be made in order to minimize the total cost. So any problem satisfies all 3 assumptions called assignment problem and can be solved by extremely efficient by algorithm designed specifically by assignment problems. So we give the general of assignment problem. The general model of assignment problem is this model. We notice in this model, the objective function is minimize j, sum from I to n, sum from I to j to n, Cij, Xij, and the subjective is, constraint is sum from I to n Xij equal to 1. This means each worker only finish one task. Sum from j to n Xij equal to 1. This means each task need only one worker to finish it. And the decision variable Xij is all binary. So this model is BIP problem, and we solve this model by branch and bound method. But if you solve this model by branch and bound method, its calculation is relatively more large. And we compare to the translation problem, and this two model is very similar. We notice that the objective function is the same, and the constraints is a little different. We note that in transportation problem, the output is AI and the requirement is BJ. And in assignment, the output and the requirement is all 1. So this is the assignment problem model. This is the transportation problem model. So we notice that assignment problem is a linear IP problem. Notation. In general, the assignees might be employees who need to be given work assignments. Assign people to jobs is a common application of the assignment problem. However, the assignees need not be people. There could be machines, vehicles, or plants, or even time slot to be assigned task. The task need not to be job. They also could be location, production, time, slots, and so on. In the definition of assignment, the first 3 assumptions are fairly restrictive. Many potential applications do not quite satisfy these assumptions. However, it often is possible to reformulate a problem to make it fit. For example, DOM assignees, DOM tasks frequently can be used for this purpose. We illustrated these formulation techniques in the example 2. Now we see example 2. the job shop company problem. The job shop company has purchased 3 new machines of different types. They are for available locations in the shop where a machine could be installed. Some of these locations are more desirable than others for particular machines because of their proximity to work centers that will have a heavier workflow too. And from these machines, therefore, the objective assign the new machines to available location, minimize the total cost of materials handling. And the information of this problem is listed in this table. In this table, we notice that there are 3 machines can be installed in 4 locations. Location 1, location 2, location 3, and location 4. And this number is the cost. The cost data for job shop for machine 1 installed in each location. In this model, the objective is to minimize the install cost. So we set the decision variables. We set xij equal 1, machine I installed in location J, and xij equals 0 is otherwise. We notice that this is x11, x12, x13, x14, and continue x44. And each xij means that machine I installed location J. And this number is the cost xij equal to 1. And we note that it is bar. This bar means that machine 2 could not be installed location 2. And the objective is to minimize the total install cost. We use this number, this cost number, to times the decision variable. So we get the total objective cost is 13x11 plus 16x12 plus 12x13 plus 11x14 and so on. And in this problem, the objective is 2. We notice that there are 3 machines, but there are 4 locations. So we write the content is x11 plus x12 plus x13 plus x14 equals to 1, means that location machine 1 means machine 1 must installed, but locations for more than machines. So this is the less than or equal to 1. That is, the workers is less than tasks. So the equality is less than 2, and this is the inequality. This is the model of this example. Now we introduce example 3, assigning products to plants. The batch product company has decided to initiate production of the 4 new products using 3 plants that currently have successful production capacity. The products require a comparable production effort per unit, so the available production capacity of the plants is measured by the number of units of any product that can be produced per day. And the information of this program is listed in this table. And we note in this table, this is 3 plants. This is 3 plants. And this is the 4 products. And the last column is the capacity available of each plant. And the last row is production rate, means production requirements. Management now needs to make a decision on how to split up the production of the products among plants. Two kinds of operation are available. Operation 1. Permit product splitting where the same product is produced in more than one plant. Operation 2. Prohibited product splitting. Now, we notice that the key advantage of Operation 2 is that it eliminates some hidden costs associated with product splitting, including actual step cost, distribution cost, and administration cost. Therefore, management wants both operations analyzed before final decision is made. For Operation 2, management further specified that every plant should be assigned at least one of the products. Now, we analyze this problem, and we notice that Operation 1 can be split the production products. So, Operation 1 leads to a transportation problem. Operation 2 is not split, so it leads to an assignment problem. Now, we formulation for the Operation 1. With product splitting permitted and the problem is a transportation problem. We solve this problem by Excel, and we note in this table, the decision variable is x11, x12, x13, x14, and this is each product produced in plant 1, and this is x12, 22, 23, x24, and x31, 32, 33, and 34. That is the decision variables in this problem, and the objective is use this unit cost to sum the amount of products. We get the objective value is objective function is minimize. Use this table number to sum the decision variables. And the constraint in this problem is the capacity limited. So we write as this is plant 1 production and less than or equal to 75 capacity production, and this is plant 2 production, and the last one is plant 3 capacity production limited. And each product, the requirement is 20, 13, 13, and 14. So we write the constraint is these variables to equal to requirements. Some these variables to equal to these requirements means each product must meet the requirements. So this is the transportation problem because Xij is any split and Xij is any greater than or equal to serial number. So this is the transportation problem, and it's solved by simplex method and by transportation method. Formulation 2. Without product splitting means that Xij means must be integer or be binary. Each product must be assigned to just one plant. Therefore, producing the product can be interpreted as a task for assignment problem. And we also solved by Excel. This is the unit cost. And model this problem, we first do some calculations. We use this column times the requirements, and we get each product produced in each plant I need a total cost, and use this column times this requirement, and we get this column, and use this column times 13, and we get this column, and use this column times 14, get this column. So this table is the total cost, each product produced in each plant. So in this model, we set Xij is 1, 0. 1 is product produced in plant J. Otherwise is 0. So the decision variable is x11, x12, x13, x14, x21, 22, 23, 24, 31, 32, 33, x44, and this is the binomial variables. It is equal to 1 and 0. And the objective function is use this table total cost 2 times the decision variables. And constraint in this program is plant. This is 2 supply and 1. And we note that plant 1 and 2 is 75 production. So it can produce this, or this. So it can produce 2 kinds of products. So the supply is 2. On plant 3, its available capacity is 14,000. So it is only can produce only 1 product. So we get the requirement constraint is sum these decision variables equal to 1, and the supply constraint subject is sum low decision variables less than supply. So we get the model of this program. It is the formulation of operation to minimize the total cost, and Xij is the binary variables, and this is the supply constraint, and this is the demand constraint. That's okay in these lessons. Thank you very much.